Start the recording again. Okay, here we go. We're back in business. Sorry about that. As I said, my co-host accidentally ended the meeting, so hope everyone can hop back on here. Okay, so yeah, most people don't use the $100 budget, all of it, but it's there in case you need something that's a little bit fancy, a little expensive. Most projects are pretty cheap. You might make oobleck, and that's just cornstarch, water, in a big tub, anything like that. Okay. Let me full screen and full screen this. And we're switching over to the lecture notes now. So we're still talking about fluid statics. And we're talking about pressure measurement basics. So sections 2.5 and 2.6 in the textbook and different kinds of manometers. All right, we're going to start off with an example, an important example of blood pressure measurement. Just going to stop the share for a second because I realize I need to share my actual entire desktop. And here we go. So you're going to watch two very short videos, and they're on Sphygmomanometry, really hard to say 6-syllable word in fluid mechanics. And it's blood pressure measurement, right? So you go to the doctor, usually a nurse checks you in, puts the cuff around your arm, squeezes your brachial artery, and uses a dial and a pump to take your blood pressure. So we'll learn how that's done. And then afterwards, we'll watch a short video where we listen to the Korotkoff sounds. And as you watch these videos, I just want you to think about the physics and think about the physiology and try to notice two interesting things. And then if I can manage it this time, we'll do breakout rooms and you can exchange your two interesting observations about physics and physiology. All right, are you seeing the YouTube video loading?
Yes.
Great, thank you.
Well, this is how you measure blood pressure. You start out, you put the cuff around your brachial artery, the stethoscope right here, so you can listen for the sounds. And this is how your arterial blood pressure is. So the first thing you're going to do is you're going to inflate the cuff. And you're going to inflate it past the level of pressure that is past the arterial pressure that is in the artery. And then you're going to reduce the pressure in the cuff. That's when you start hearing the sound. And the number at which you hear the sound at first, that's going to be your top number. Note the sound comes from the restriction over here. And then when you reduce the pressure below the arterial pressure, the sound goes away. And that's it.
All right. Okay, so that is the first video, and I want to back up here and just, can you see the cursor? And just point out that we have a manometer here, which we're going to be learning about today, okay? So this is just a vertical column of fluid, and the height of the column tells you what pressure we're getting in the blood pressure cuff. And this is actually done in this case with the height of a column of mercury. And that's the reason that your blood pressure is taken in units of millimeters of mercury. It's actually the height of that column. All right. Next one here. This is what you hear as you do this as a clinician. Now the demonstrator is inflating the cuff to a pressure above systolic, the high number. You don't hear anything yet. All right, so I'll end it there. So what we saw was inflating the cuff to a very high pressure, cutting off the brachial artery, and then releasing the pressure until you heard the first sound, and that was the systolic pressure, the high number, and then continuing to release the pressure until you heard no sound. And that was the diastolic, the low pressure. So I hope you made two observations, either about physics or physiology. We don't have a ton of time, so I'm going to put you in breakout rooms for just 1 minute. And go. Hi, welcome back. We're slowly trickling in from our breakout rooms. About half of you are back in the main room. Those still in breakout rooms have about 30 seconds left. 10 seconds, and then we'll just share if a couple people can share some observations. 4, 3, 2, 1. Okay. So everyone should be back from the breakout rooms. Welcome. I hope you were able to exchange a couple of key observations. Does anyone want to share something? Right. People are feeling a little shy today, so while people are waiting, I'll ask you if during the first video, did anyone notice that by the cuff in the cartoon of the brachial artery, every time the cuff was pressurized, there was a little white scribble. Seemed like something happening when the cuff was pressurized. Anyone notice that? So what actually makes the Korotkoff sounds is the fact that you're constricting the blood vessel, right? So normally you would have a nice laminar stream of blood flowing through your brachial artery, but you constrict the blood vessel and you get turbulence, right? And so that's what leads to those sounds. So the white scribble was actually supposed to, in the cartoon, was supposed to signify that you have turbulent streamlines. So you have chaotic motion of the fluid particles rather than really smooth straight lines. Any other observations from the video? All right. One other interesting thing was the pressure waveform, right? It wasn't just sinusoidal. It was mostly positive pressure with a sharp peak and then sort of a dent and then a second sharp peak near the maximum pressure. And that's actually due to the elasticity of the heart and the tissue surrounding the heart and the arteries. There's a little bit of bounce back, and that leads to that second peak in pressure. All right, let's turn now to the content from chapter 2 that we're covering today, manometry.
Hi, I was wondering, which of those pulses is the one that gives you the measurement of your blood pressure?
Yeah, that's actually really interesting because it's not the very maximum blood pressure as you saw. It's a little bit below. It's actually based on when you can begin to hear the noises, the Korotkoff noises, right? And as you saw in the video, the line, the pressure line, was a little bit below that maximum peak when she recorded the systolic pressure. So the systolic is a little bit of an average maximum pressure. Diastolic is a little bit of an average minimum pressure.
Thank you.
Thanks. All right, I'm going to end sharing and turn over to the slides. So if you've got the slides with you, you can bring them out. All right. So can everybody see the slide that says today, video projects, Dr. Christine Burgoyne?
Yes.
Great,
Yes.
thank you. Okay. So a little bit about the measurement of pressure. I really want to enforce the idea of gauge pressure, right? So let me full screen here. So there are 3 concepts to have in mind when it comes to pressure: absolute pressure, atmospheric pressure, and gauge pressure. And the way that those three are related is that the absolute pressure is equal to the atmospheric pressure plus the gauge pressure. Okay, and if you look at this figure over on the right, you can think of the floor as zero pressure, right? Imagine if we were able to have a true vacuum with zero particles inside, so nothing bombarding against the walls of the container to give rise to a pressure. And the pressure increases with height from the floor in this figure. Okay, then look at this second shaded bar here, which is the local atmospheric pressure, right? So this is, we leave our house, walk outside, or even inside. This is the pressure that we experience. You know, we've got air molecules bombarding against our skin constantly, giving rise to an atmospheric pressure. So this is denoted P atmospheric. And this is 14.7 pounds per square inch, or 760 millimeters of mercury, if we're thinking about measuring it the same way that we measure blood pressure. For the purposes of this class, we assume a gauge pressure. If we're given a pressure, we'll assume it's a gauge pressure, unless we're told otherwise. But here, we've got our atmospheric pressure here, and then we've got a gauge pressure, which can either be positive, so it can be above atmospheric pressure. Let's say you've got a chamber, you pressurize it above the atmospheric pressure value, then you've got a positive gauge pressure, like you have at 1 here at the top, or you can have a negative gauge pressure, which just means the pressure in your container or your system of interest is lower than atmospheric pressure. You can never, ever have a negative absolute pressure. Right? You can get down to 0, you can have 0 gas particles in a container, you can't have negative gas particles, right? Okay. Another thing I want to mention is barometry. So that's the measure of atmospheric pressure. And it comes from the Greek. Apparently baro means weight in Greek, so, and meter means measure, so weight measure. And so if you imagine that you've got a tube of mercury open on one end, and you turn it over, so it's closed at the top like you see here, and the bottom is connected to a pool of mercury that's open to the atmosphere. Well, what you would develop in this column of mercury is a balance of pressures, with atmospheric pressure acting up from the bottom, the vapor pressure of the mercury gas that develops in that closed tip at the top is acting there, and then we have the weight, right? So if we do a force balance, we see that the atmospheric pressure is equal to rho h plus the vapor pressure. But vapor pressure tends to be very small compared to the type of pressure that develops in this column. So this is basically equal to rho h. So this is how you would one way that you would measure the pressure in the atmosphere. Generally speaking, high pressure in the atmosphere is good. Low pressure, so when it drops from a typical value by about 10%, is bad. It means that there's some sort of weather event that's about to happen. Just a note here, if we were to measure atmospheric pressure, so standard atmospheric pressure is 14.7 psi, A, and that A means absolute, you would need just 29.9 inches of mercury but you would need 34 feet of water to do the same thing. And you see that reflected in this figure on the right. And that's because mercury has a much higher density, right? So you can get it has a much higher specific weight. And so you can get much larger pressure differences with a small h, a small column height. All right. First type of manometer we're looking at today is a piezometer tube. This is governed by fluid statics. So you can see, looking at the figure over here, you've got a tube that's open at the top, open to the atmosphere. So that's atmospheric pressure. You've got the height of a column of liquid. We know that the pressure in a fluid only depends on the height or depth, not on lateral distance. So when we move from this point 1 over to A, there's no change in pressure because we're at the same elevation in the same fluid. So we can write down the equation for this piezometer to be PA is equal to gamma 1 H1. There are a couple of drawbacks to using this, and the biggest drawback is that it can only be used to measure positive gauge pressure. And it can only measure the pressure in liquids because it's open to the atmosphere. So if there were gas, it would escape. All right. So to solve some of these problems, we turn to a U-tube manometer. And this allows us to introduce a gauge fluid. So looking over here, we've got some fluid with specific weight gamma 1 here at point A. And we see if we follow the tube around, it's open to the atmosphere at the top. But in between, we've got this pink shaded gauge fluid, and that's a liquid, but the fluid in A, fluid 1, can be a liquid or a gas, right? So this gives us now the freedom to measure pressure in gases. So how do we go ahead and see what the pressure is at A? Well, we walk through the manometer starting at point A. So first, we see that the pressure at A is equal to P1 because point 1 and point A are at the same height in the same fluid. Then as we go from point 1 to 2, we use our hydrostatics equation to say P2 is equal to P1 plus gamma 1 H1. As we go from 2 to 3, we see that P3 is equal to P2. Why? Because they're at the same elevation in the same fluid. Finally, the atmospheric pressure is equal to P3, this time minus gamma 2 H2. And the minus here is because we're traveling upwards instead of down. So when you go from a point that's higher to a point that's lower, it gets a plus sign. When you go from a lower point to a higher point, it gets a minus sign, right? That's from our basic hydrostatic equation. All right, so here, PA is equal to atmospheric pressure minus gamma 1 H1 plus gamma 2 H2. And that's equation 214 in the textbook. All right, I have to stop there because it's 2:15, but I will annotate the remaining slide. Let me stop sharing for now. And let me hop back over to the slides. to just wrap up for today. Okay, so looking forward to Wednesday, we're going to look at hydrostatic forces on plane surfaces, underwater, or another liquid. We're going to finalize the buddy groups this week. And then remember, in about a week and a half, we've got our first exam coming up. I've outlined here the basic parameters, but I'll talk more about the exam in the coming lectures. So it's 2:15. Feel free to log off. I'll stick around in case anyone has any questions.
Hi, I have a question. So I am a little bit confused still about gauge pressure. And, where's it coming from? Is it like within a closed space or?
Yeah, so the gauge pressure is whatever pressure you have that's above or below atmospheric pressure.
Okay, so if I'm like staying in my room right now, it will be like atmospheric pressure.
Yeah, you're experiencing atmospheric pressure in your room, right? So you could develop a small pressure difference from atmospheric pressure. So for example, if you were to open the window and air were to rush in or rush out, that means that you developed a small negative or positive gauge pressure.
Okay, so it's like when that's like when I'm opening to a new, some new fluid, or?
Yeah, so anytime, so you have to, yeah, so you're right. So in order to develop a pressure which is different from atmospheric pressure, you have to be closed off from atmospheric pressure, right? So you have to have a container, you have to have a room, and everything is shut in the room. Once you are sealed off from atmospheric pressure, you can then go ahead and pressurize or depressurize whatever is in that container. And I mean that really broadly. You know, we could be talking about a tank of gas, we could be talking about a soda can, right? You open a soda can, for example, and you have a really high pressure inside the soda can that develops compared to atmospheric pressure, particularly if you shake it.
Oh, okay, so if I shake the soda bottle, I'm so sorry, I'm taking this.
No, this is what I'm here for.
The gas that builds up is going to be causing gauge pressure?
Yes, yes. So if you were to somehow shake a soda bottle, keep it closed, but manage to measure the pressure inside, you would see a pressure that's higher than 14.7 psi, which is standard atmospheric pressure at sea level, right? If someone asked you, what's the absolute pressure in the soda can, you would say 14.7 psi plus the pressure I just measured inside. If someone asked you, what's the gauge pressure in the soda can, you would say the pressure I just measured inside without adding the 14.7 psi.
That clears up so much. Thank you so much.
You're absolutely welcome. And remember, you can have a negative gauge pressure too. So if you capture some atmospheric air and then depressurize, create a vacuum pressure, you can actually then measure a pressure that's lower than 14.7 psi.
Okay, thank you so much.
You're welcome. Any other questions? All right.
Yeah, real quick. The YouTube manometer, I don't know if I said that right. For the fourth step, why is it minus the?
Yeah, great question. So pressure increases as you descend in a fluid. If everything's still, we're dealing with hydrostatics. If you descend in depth because of gravity, the pressure increases.
Okay.
So when we were first tracing around the YouTube manometer, we kept going down, 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 or over. Then in that last step, when we got the minus sign, we went up.
Okay.
We went from a lower point to a higher point, so we needed to have a negative sign there instead of a positive sign.
Great. Thank you.
You're welcome. Any other questions?
So therefore, anytime we measure the pressure in the liquid or like under the sea, so we when it is open to the space, we never consider the pressure on the top. We just make it zero because we're measuring the gauge pressure.
Usually, yes.
Yeah, but whenever he mentions something that it is not open to the air, we have to consider that pressure above the sea level, they just say. So whenever it's open and we're measuring under the sea, we consider it zero because we're measuring the gauge pressure.
Yeah, that's true. But usually in most problems in this class, you're just concerned with gauge pressure. There will be certain times when you have to care about absolute pressure, but usually the problem will say it.
Yeah, but in the problem in the last week we have problem, and if he mentioned that it's closed and mentioned some pressure above the liquid, we consider that pressure. But if it was open, we never consider it. If it's open to the space, we never consider the pressure.
Yeah, that is true in general. If it's open to space, if you have a liquid and then it's open to the atmosphere, like the top surface of the ocean, then you would say that the pressure is equal to zero there.
So about the midterm, it will be about chapter 1 and 2.
The exam will be chapter 1 and then chapter 2 through section 2.8. So we have one more topic to learn for the exam, and that's hydrostatic forces on planar surfaces.
Okay.
We'll be talking about that Wednesday.
Sorry if I asked you, I asked you before, can we have the formula that we will have it on the test so we can practice when we're reading? Because,
yeah,
you know,
you're more than welcome to have a formula sheet if you'd like.
Yeah, yes. How we could find it, the formula sheet? You already uploaded it or you will?
I don't provide a formula sheet, but if you want to look through the textbook and write down what you would find useful, you're welcome to do that. I have a recommendation. Give you a recommendation. You'll notice that at the end of every chapter, there's a chapter summary. So for example, this is the summary for chapter 1. And there's a box that contains all the important formulas from the chapter.
Yeah, so you mean that we have to make our formula sheet?
Yes, I don't provide one. And now I understand what you were asking me last time.
Yeah, sorry. Maybe sometimes I didn't ask and didn't understand it the right way. Therefore, I'm asking so much. Sorry for that.
No, not at all. Not at all.
Sorry. Thank you very much. Now it's so clear for me. Thank you.
You're welcome. I'm so glad.
Thank you. Bye-bye.
All right. Is that any more questions? Or are we all set?
And the last one is for a group. I just have to wait to know what is the members of my group.
Yeah, there's one group I haven't finalized yet. So once it's finalized this week, I will publicize all the groups.
Yeah. Okay. Thank you very much.
Thank you.
Thank you. Bye.
All right, everyone. I'm going to sign off here. Thank you. We'll see you on Wednesday.